Okay, thank you.
Well,
Could I share my screen?
Please give me 1 minute to present you and Mohammed, and then I will give you the hand to share your screen and start the presentation. The topic is 3D geostatistical temperature modeling of Germany using Isatis.neo. Dr. Thorsten Agemar is a geoscientist and has been working at the LIAG Institute for Physics, Hannover, Germany, since 2006. In 2018, he was appointed as a research lead for information systems at the LIAG. His main tasks include project management and programming related to the web-based geothermal information system, GeoTIS, as well as 3D modeling of geology and subsurface temperature. He has been using Isatis software for the latter since 2021. Second presenter, Dr. Mohammed Anis, has been working at LIAG since 2024 as a geoscientist in the Warm Good project. This project focuses on the uniform provision of geoinformation on near-surface geothermal energies across Germany. His primary responsibility is the enhancement of the 3D temperature model in GeoTIS, which involves conducting geostatistical analysis, thermal modeling, GIS mapping, and spatial analysis. Prior to joining LIAG, he completed his PhD in geosciences from the University of Göttingen, Germany. His doctoral research focused on the geothermal exploration in the crystalline basement of Himalaya and Karakoram regions of Pakistan. Dr. Thorsten Mohammed, the floor is yours, please.
Okay, yeah, thank you very much for the introduction. I will share my screen. I will start with the presentation and then I will give over to my colleague, Mohammed Anis. So I hope you can see my screen now.
Perfect, thank you. I see.
Okay, yes, so we are both working at the LIAG Institute for Applied Geophysics, which is located in Hanover, Germany, on the campus Geocenter Hanover, where also you could find the BGR, the Geological Survey of Germany, and the Geological Survey of Lower Saxony, the LIAG. And yes, our institute was founded in 1999. Currently, we have 105 employees, so we are a rather small research institute. And yes, our history dates back back to 1948. So it was founded by the idea to concentrate the common tasks of the geological surveys for each federal state in one institute or one department. And that was located later on at the Geological Survey of Lower Saxony. And geophysics was a major part of these common tasks. And yes, in 1999, we became an independent research institute. But still, we have strong links to the geological surveys in Germany. Our institute, yes, geophysics. Our department has a strong focus on geothermal energy. In the past, mainly deep geothermal energy, going down to 5 kilometers. Recently, also investigating research in the shallow geothermal, which is based on heat pumps and extracting energy from soil or shallow subsurface. Yes, but besides that, there are also other departments also by our institute related to seismic, as I mentioned before, and but also numerical modeling, and also geo-risks like sinkholes, hill slope sliding, and drinking water resources, especially in coastal areas. So there's a wide variety of different research topics. You're welcome to look at our website and see what we're doing. But yes, in comparison to our the previous presentation, our institute focused on terrestrial issues or research topics, so not marine. Okay, so that was just a brief introduction to our institute, and now would start with a brief introduction to the topics. Yes, it's about subsurface temperatures, which is an important parameter for assessing the geothermal resources below our feet. So the higher temperature, the better, the more energy we have. Could be the reservoir could be just the soil or hard rocks or some aquifers. We have shallow aquifers, deep aquifers, and the water we tap might have temperatures between 9 centigrade and up to 150, 160 centigrades. And there are a couple of, around about 100 sites where we tap in very hot waters above 40, 50 centigrade, and which is then used, for instance, for district heating networks or even for geothermal power production. So yes, and the records of subsurface temperatures also go back to the 50s of last centuries. So there's a long research tradition in the temperature field of Germany. And yes, covering both geostatistical and numerical modeling in the past few decades, using this available information and available data since 2008, 2007, 2008. We started with looking more towards 3D than just 2D maps. So that showed us that when we used a methodology based on 3D, we could incorporate more data and get better results than just using 2D methodology. Okay, since 2002, we have Geophysics Information System, a public database and information portal that provides data. Geophysics data are not just temperatures, but as you can see here on the starting page of the geoelectric data, gravimetry, magnetics, transient electromagnetic data, all kinds of data related to methods about subsurface exploration by geophysical devices. And on the right side, see a map of Germany with a it's maybe not up to date, but shows pretty much the distribution of borehole and mine temperature data we currently have. So, and this map shows the challenges we face. So we have first heterogeneous distribution, so they're not evenly distributed. Some areas there are dense. We have high density of data, whereas in other areas we have low density of data. The coloring shows the depth level of the information. So yes, in some areas we have deep information, and especially in the middle of Germany, in the highlands area, we have very little deep data, mostly shallow data. Generally, we could say we have more shallow data, like up to 1,000 meters, compared to data that's going deeper than 3,000 meters. There's one well in the northeastern Bavaria going down to 9,100 meters. It's the deepest well in Germany. But yes, as you can see, most of the deep wells are somewhere between 1,000 and maybe 4,000 meters deep, and they originating from the hydrocarbon industry. And yes, the distribution of the data points from the boreholes reflect the interests of the hydrocarbon industry. They're looking at the deep basin structures, like the North German basin in northern Germany, the Upper Rhine-Graben rift system, but also the North Alpine Foreland basin here, which we call the Molasse Basin. So here we have some deep information in these three areas, and in other areas, data is limited to rather shallow depths up to maybe 1,000 meters, mainly. Also, the quality here we have like A, B, C differentiation differs a lot. Large symbols show high quality with little uncertainty, but in many locations we have poor data in terms that what we call the buttonhole temperatures. Because oil and gas industry normally was not so much interested in the temperature, so they just measured the temperature shortly after drilling has stopped, and with the drilling process, the drilling fluid is circulated in the borehole, causing cooling, which is necessary also, of course, but also the cuttings from the drill bit are lifted up with a drilling fluid. So, and if you don't wait at least some weeks, you will record temperature that is much affected by this drilling process. There are correction methods that are also implemented in the geophysics information system. They're based on long research on this topic at our institute, and they're also described in the literature. So there are various correction algorithms, and in this information system there are various algorithms implemented, and basically a strategy is applied that based on experience to get the best out of the data. Okay, we have around about 11,000 boreholes with temperature records, and so some temperature records from tunnels or mines. Especially regarding the very shallow data, these are of course not so much in the focus of the hydrocarbon industry. That is like between 0 and 400 meters. We have very few data that look specifically at this depth range. This is something where Mohammed Anis will later also go into more details. Okay. And so for the development of the subsurface temperature model, we have currently this workflow. We compile all the available corrected and validated data from the geophysics information system. And we add also some ground level data. That's basically meteorologic data to get yes, the soil temperature, and this is then used for 3D universal kriging modeling. So we produce a grid with a lateral 2 by 2 kilometer resolution, and in the vertical dimension 100 meter, and it goes down to 5,000 meters below sea level. Since in most areas we have a rather conductive regime that controls the temperature distribution in the subsurface, negative gradients, so like a decrease in temperature with increasing depth, is rather unusual and is considered in most cases as artifact. This is different from active volcanic areas, like for instance Iceland, that you could indeed find negative gradients, but we remove the negative gradients because yes, we don't have any active volcanism, so that can be excluded. And yes, we are also creating virtual logs. I mentioned the bottom hole temperatures, but there are also, of course, log data that go that are recorded all the way down from the top to the bottom. This is, of course, better, but yes, for hydrocarbon industry, time is money, so they reduce the time for measuring, doing just single measurements at some point during the drilling process. Mostly, of course, at the end of the drilling, at the very bottom, but could also be after some casing. So there could be at different depths some bottom hole temperatures, maybe 2 or 3, but usually at least 1 at the very end of the drilling. And these are then interpolated to the surface temperature as virtual logs. That gives some benefits. I will explain later why this is a good idea. Yes, the next step is then the model validation. We look at results, and then we project these 3D temperature model on geological horizons, particularly those that are very interesting for the geothermal industry or geothermal energy usage. And then we do a conversion of the data to a binary format and store the data as binary large objects in our database, and so make them available for our geotists, which could be seen as a public digital geothermal atlas for Germany, showing various data, geology, exploration data, and also permits and location of boreholes, of course, but also, the temperature on specific geological horizons, or also in cross sections that you can create interactively by setting points on the map. If we have time, maybe I could show you live from this, because it's it's available on the internet. Found it at www.geotis.de. Okay, come to the next step. So why virtual logs for bottom hole temperatures? Sometimes happens that we have shallow boreholes with strong gradients next to deep boreholes with not so strong geothermal gradients. The average geothermal gradients is around about 30 centigrades per kilometer. And as you know, when you do kriging, we have a range that is giving the area of influence, affected by the measurements in the statistical process, and so that could result in a negative geothermal gradient between the bottom of these two wells, and so we need basically virtual data points along the drill path from the top to the bottom to avoid this problem with negative temperature gradients caused by the grading process. Yes, in northern Germany, the range is quite high, several tens of kilometers. And yeah, that is the problem we try to circumvent with the virtual logs. On the right side, you show some temperature depth profiles. In most cases, this increase of temperature with depth is quite linear, somewhere between 25 and maybe 40 centigrade per kilometer. But in some areas, especially in the upper Rheingraben, we see strong deviations from this linear path. For instance, here in Landau, this the gray curve, also Subsurface, also upper Rheingraben, but on the French side. See here, steep increase in the temperature, and first 1.5 kilometer, but then with greater depth, it's approaching again back to the normal gradient. So this is related to upwelling of deep groundwater, so groundwater that has been heated to high temperatures in the deep subsurface, and due to changes of the hydraulic head, it could cause at some locations along fault zones or fracture zones where we have fluid pathways that go in vertical, more or less vertical direction. We have this upwelling and this positive temperature anomalies, as you can see here. Okay, so but this is not always the case, and it depends on the area, on the geology. Besides, there are also different thermal conductivities in the subsurface. But yes, this hydraulic special case is what we have to consider, because so when we want to do a 3D subsurface temperature geostatistical model, this criteria of stationarity is not maintained, is not fulfilled for all Germany. So what we did is we split Germany in 3 parts, and so one part is southwest Germany with the upper Rheingraben. You see, hopefully you can see here very high red areas with high temperature anomalies. But also Bavaria here, southeast Germany, we have some strong lateral gradients. We have a negative temperature anomaly east of Munich, for instance. This might be caused by advection of deep advection of groundwater, but it's currently still ongoing research in this topic. And yes, we also see the North German area has some variation of temperature. So this is here in 3 kilometers depth, or 3 kilometers below sea level, I should be more precise. And so that means we have 3 different semi-variograms for the 3 areas. And yes, the ZIL here is highest for Southwest Germany due to the upper Rhine-Graben. It's lowest for Northern Germany and yes, Southeast Germany, and we also included this part here of the Molasse Basin in Upper Austria, because it's also very relevant for deep geothermal energy usage. And Geological Survey of Austria asked us to do so and gave us some data. So yes, this is higher than Northern Germany, the ZIL, but not as high as the Upper Rhine-Graben. Also, the ranges differ. We have a range of about 90 kilometers for North Germany and just 30 kilometers for the southwest of Germany. And yes, this is of course important. And when we consider also the different certainties of or different qualities of data, yes, we are within that range. We have, yeah, the Isatis needs to balance basically, yeah, the weighting of sampling points regarding uncertainty and distance. Yes, here are some more details about the nugget and also the range vertical, which has been deduced from log interpretations. We use a spherical variogram model, as you can see also in the plot. Yes, also another problem is that spatial variance changes with depth. We have lower spatial variability at 1,000 meters compared to 2,000 meters or 3,000 meters. You could see that here the sigma is called, could say, the Viking standard deviation. It's even declining a little bit here for the Upper Rhine-Graben. It's very deep, as you remember from the temperature depth profiles. At greater depth, deeper than the upwelling zone, the temperature profiles approach again the normal gradient of around about 30 centigrade per kilometer. So yes, this is also another challenge. So we're thinking about finding defining the domains of stationarity. So currently we have basically just 3 boxes, but yes, in the future we might think about optimizing our methodology in terms of using different variograms for different depth ranges. Also, not using exactly rectangle boxes, but maybe boxes that are related to the plate types, that are more the boundaries defined by geology. So that would also, I think, give some improvements, especially for the assessment of uncertainty, because that is also something that industry asks for. They not just only want the temperature estimate or a temperature prediction for a specific spot or specific depth. They also want to know what is uncertainty. So in order to assess the exploration risk. Yes, up until 2019, we've been using the Gokert software for all the geostatistics. And the Kokaskur software is not really a geostatistics software. It has the GSLib library included. We use it mainly for 3D geological modeling, and for this purpose, yes, we still use it. It's no complaint about it, but yes, we realized that the features regarding geostatistics are not enough, and yes, this caused some problems also. Didn't produce so good results if we didn't apply the normal score transformation to the data. Also, the temperature data are quite fitting Gaussian distribution. And yes, with the normal score transformation, we had conversion to values from 0 to 1, and we had to calculate back the uncertainty, and it was all not really very good. But the major drawback was we could not include the uncertainty, the different uncertainty or the different quality of the data. And this caused us to apply some filtering. So in areas close to good data or high quality data, we filtered the poor data from our data set. So losing basically information just to avoid that poor data overrides high quality data. So that was like a 3-stage filter. Excuse me. So a 3-stage filter to get to consider the different qualities. Yes, but with Isatis, we then started with the 2021, 2022, and also offered us other more options, especially when looking declustering by sectors, and also as we have more data in the shallow and less data in the deep. So because yes, the deep data boreholes also provide data of less deep domain. Data gets scarce as deeper as we get. So, and with Isatis, we were able to define a maximum number of data points that come from above or from below the rigging estimate location. So yes, we see a lot of advantages, and I will show you some comparison. Here for the southern Germany, for the upper Rhine-Graben, see also the Molasse Basin here in this area. And on the left, you see now the new model, and on the right, you see the old model. Yes, in the 4 years, some new data points have been added, especially in the Munich area, which is about here. But because since we don't need to filter anymore for quality, just give the different quality in terms of standard deviation to the input data, we have a lot more data, and you see it from the model results. It gives a much more detailed view on the subsurface temperature here at 2 kilometers depth. So that is much better. But also you can see some areas have where there's no data. We see a shift in temperature here towards lower temperatures. But yes, also in the upper Rhine-Graben, the temperature anomalies due to better data density, we see that these positive anomalies are much more confined, much more local, not so wide as we previously assumed. And also, we've seen this in reports of geothermal exploration that some new projects, the project developers didn't achieve the temperatures, or didn't see the temperatures they expected. So yes, I think this is a major quality increase. I forgot to mention the coloring. The gray dots refer to temperatures in the depth range 1 to 2 kilometers, and black is above, or should say below 2 kilometers depth. So they are, of course, more meaningful. Okay. And we did this also in a histogram here for the upper Rhine-Graben area. And yes, due to the fact that the positive temperature anomalies are much more confined, we see a negative deviation when we compare the two models. So the new model is a bit cooler. Also for northern Germany, we did this same procedure. We have the North German basin, and here in the North Rhine-Westphalia, the Münsterländer Kreidebecken, Münster-Kreide basin. Here the differences are not so strong and not so marked as we've seen for southern Germany. It's pretty much the same, but yes, of course, when we look close, you also see some deviations. It also gives more details due to more higher data density. And when we look at the histogram, so what we see, the deviations for 1,000, 2,000, and 3,000 meters below sea level, it's in the range of mostly -4 to +4 centigrade, which yes could make the difference for the economic viability, but it's not so pronounced as we've seen in the slide before with upper Rhine-Graben, where we had deviations of sometimes 10, 12 centigrade or even more. Okay, so this is a bit of a summary what we have found out. So yes, we use universal 3D kriging, gives us best result, best prediction of the subsurface temperature in unsampled locations. We make strong use of the declustering, especially with the balancing of deep versus shallow, or above or below the prediction point. Yes, accounting for data uncertainty is very important. We assigned, based on some statistic research, especially in areas where we have both VHT, buttonhole temperatures, and other high-quality data. So that gave us the opportunity to assess the uncertainty of each data point. And so that resulted in much better 3D temperature assessment. So, and now I would like to give over, and Mohammed, I will press next when you say.
Yeah, okay, thank you.
So,
thank you, Torsten and Bertram for this, inviting us for this presentation. I will introduce about the Warming Good project briefly, that this is quite a recent project, in fact started in late 2022, in which the objective was to overall harmonize the subsurface data, which is closer to the surface, like less than 400 meters. So because here the shallow geothermal energy, in terms of making it more accessible and more providing the information in a more homogenized fashion to the public in form of and uploading this information in a GeoTIS finally. This is the objective. So in this regard, that the idea is to acquire the data from the different state geological surveys, because having 16 different states and each state having different laws and regulations and their restrictions on the exploiting the subsurface for the near-surface geothermal energy. So it makes quite confusing, especially for a normal public user. So the idea is to acquire the data, to harmonize it in a way and present it so that it can be really useful for the general public. So in this regard, one of the aspects of this is to also develop a temperature model, especially for this shallow region. Since, as Thorsten already mentioned, that the current data situation, which for which the 3D model exists, it's mostly the majority of the data points are more related to island exploration wells, which were mostly deeper. So very few information points exist at this point. And then the idea is to get acquire these temperature data as well from these state geological surveys, and then to analyze them and to assess the quality, and then like to apply a temperature correction because of the different measurement times and different measurement conditions. So all the data has to be optimized and corrected in a way that it can then used for the temperature modeling. And another thing is that since we are dealing with the subsurface information, which is closer to the surface, so there is especially the impact of different seasons, year, and also now we can say that the climate, which is warming up. So these factors also need to be accounted for as much as we can in this project. So, and then the aim is to make a geostatistical temperature model, and at the end somehow integrate it with the existing model so that we can perform have one harmonized temperature model which shows the near surface temperatures as well as the deep surface. So next slide, Thorsten.
Sorry. Okay.
Yeah. So coming up with the variables in the shallow part of the subsurface is mostly the seasonal variation due to the temperature. So the temperature normally as the average for the winter and summer season, especially, its effect can reach up to 20 to 10 to 20 meters of depth, depending upon the soil conditions. So this is, and the deviation in such temperatures could be like tens of degrees of Celsius in this variation. So which is quite important, especially in this region, because the heat exchangers or collectors in this spot which are to be installed, so they are really temperature sensitive, and for them that such variation needs to be accounted for, and especially in the upper 5 meter of the depth. Here, as you see on the right hand side of the figure, that is the temperature in this region less than 5 meter of depth, it has the highest variation between the seasons. And also we have, which is not shown in this figure, that if we have the effect of rainfall or groundwater percolation, then this effect can reach up to 50 meters of depth in this in such a region, and also in the regions where there is high topographic gradient. So, for example, if there are mountains and with valleys, so there that the shallow subsurface temperatures are more affected by the seasonal variations. So the idea is to account these variations as well. Next slide.
Why is it so? Sorry.
So the first, in this regard, collected German weather service DWD data. Well, so they have these around 300 locations all around Germany, from which, although they use the air-based temperature, which is collected 2 meters above the surface, but they have in the soil different sensors like moisture and different thermal physical properties of soil, which they collect the real-time information. And from a using of MBETI model and this air temperature, they calculate a derived soil temperature with different depths from 5 centimeter to 100 centimeter of different depths. So we treat this temperature as a high standard or high quality temperature measurements because they are hourly based temperatures, and then at the end they had this 30-year of average. But despite of this high accurate temperatures, their spatial coverage is quite limited. So as you can see that on the figure of left hand side, that we have interpolated that the temperatures, their variability is not much. So 9 or less than 9 to slightly over than 12 degrees Celsius. So this is the problem. This does not account to the variation of the topography and other surface factors like land use and different factors in this image because of this low spatial coverage. So to overcome that, the idea was to use the satellite imagery and the temperatures collected from these imageries. So in this regard, there is a MODIS satellite which provides the long-term temperature coverage from 2002 and to the recent. It has a ground resolution, each pixel representing a 1 kilometer square on the ground. So which is still not high enough for as what we wanted, 100 meter square of the resolution of the ground. But still for the testing purpose, we collected this information. The data which these satellites collect is in form of emissions, land surface emissions in form of thermal infrared imagery, and from them the surface temperature is collected. And this is like a weekly product. Every 8 days they collect one image for the last 23 years, and from this 23 years we calculated the average of all the project, and then although it has a lower accuracy, but its coverage is everywhere in Germany, and you can see that on the image on the right hand side that it shows the higher areas as well as lower areas in quite a good overall spread of the data, and also the effect of these areas which are densely populated, the cities, especially in the eastern part, where you can see that the reddish dot is the city of Berlin, and also in the southern part is Munich, and the upper Rhine area, which is also higher temperature as compared to the surroundings. So then the idea is to merge these two products in form of co-kriging. Next slide, please. For that, we need to have a correlation between the two DWD temperatures and the land surface temperatures. Although in this regard, the correlation could have been more higher, but still it's a fair degree correlation of around 0.6 terms of linear correlation. So so where we did it like a collocated co-kriging, in which the variograms, cross variograms of both raster values data are produced, the raster values which were intersected by the point data of the DWD. So, and then they were merged, and then in this image on the right hand side, that it shows that the high variability is still there, but now the temperatures, they are more closer to the for the DWD temperatures. So it kind of comes up between the intermediate product between two. But the correlation could be improved if, for example, we had a higher correlation between these two products. So that's why, because the land surface for this satellite image, it presents an area of 1 kilometer square. But in terms of the ground data, point data from DWD, it's like just on point data. So that's why the correlation could not be that much. So the idea is now to get the more high resolution data, which is Landsat 8, which has a pixel resolution of 100 meter. And we are hoping to get more good correlation from this product as well, so that then we can produce good temperature model, especially on the surface conditions. Next slide. So this is for especially the surface temperatures in this regard is quite important. So because, as I said in the previous slides, that this variation in the surface, although now we can create more, like this was the average product, although for the whole year we can now divide them into summer temperatures and into winter temperatures, and then we can extend, also get the data which we will get from the State Geological Service, and then separate it. Also depends on their acquisition times. If they were collected in the winter, then we can interpolate them in the for the winter products, and for the summer the same we can do. Especially we need this because we have observed in some of the data, of which I have not shown you here, that if the conditions of soil are porous, then seasonal temperatures, their effect can extend at the depth of 50 meters. And yeah, for the data which is deeper than 50 meter, we will have to work with this average product, average for the whole time year, and then integrate it with the existing temperature model. And we hope that this would to improve the resolution, as well as it reduce the uncertainty, especially the subsurface, near subsurface, for this shallow geothermal energy in this existing temperature model. So yeah, that's it for this warming good temperature task which we are doing for now. And I hope that in the few months from now, I'll be happy to share more results with this. Thank you.